graphing quadratics. And the first thing, I really want to emphasize the similarities between our study of quadratics and our study of lines. And part of that is to prepare you for college algebra, right? When we're going to kind of expand into other polynomials as well. So quadratics and linear are sort of our most basic types of polynomials, but there are lots of other types that we can learn to understand as well. So we kind of want to think of like lines and then quadratics and then beyond. So maybe that's part of my motivation there. Also, I just want to ground it in something that we're a little more comfortable with, perhaps, right? So if I ask you to graph a line, you know kind of all those features about lines. You know the slope, you know the intercepts, you know different forms of the equation, and how to kind of bounce around to find the things that you need to solve those problems, right? So lines are something that are very important for us, and hopefully that we understand pretty well. And we're working towards the same level with quadratics. So the first thing is to remember, when we're graphing a quadratic, we need a quadratic function, right? So rather than a quadratic equation, we're going to be looking at a quadratic function, right? And the difference there, of course, is that we are not saying that the quadratic equals a number, but we're saying the quadratic equals some output or some y value or some function value, right? So if you give this an x, you do the calculation, you're going to end up with f of x, right? And that creates a series of points. And those series of points are what the graph consists of, right? So that's what we're doing when we try and graph. And we know, I think already, our kind of basic quadratic, which is f of x equals x squared. And that quadratic looks like this. It's of course infinitely many points here, but two kind of useful or interesting points are right here, right? This one is 1, 1, and this one, right, is minus 1, 1. And those are handy points to keep track of. Again, there's lots and lots of points, but those are going to be helpful as we look at other versions of quadratics. So one perspective is to say, well, if we remember our basic quadratic, we also remember some other versions of quadratics too. If I give you g of x equals x squared plus 3, we hope you remember that that just takes my original quadratic and just shifts it up 3 units. Right? Every point moves up. And again, keeping track of these kind of points, those can be referenced from the vertex, right? This point down here at the bottom, this is called the vertex. Right, and in many ways, it's kind of the most important part of the quadratic, right? Or this parabola, that's the shape. What about g of x equals x minus 2 squared plus 1? Well, again, hopefully you can remember your transformations there. The minus 2 is going to shift the graph over to the right 2. And the plus 1 is going to shift the graph up 1. Since the vertex started at 0, 0, it's easy to sort of keep track of where the vertex is, and the rest of the parabola follows along with it. Again, just like before, those kind of reference points over 1 and up 1 from the vertex also move with the same relationship. These are just sketches, right? They are not perfect representations of the parabola, but they show the sort of important features and give us some relatively similar values. If we sort of continue these transformations, what we can do is develop kind of a generic form. All the different types of moving and stretching can be condensed into this form. This is called the vertex form. And it's called the vertex form because I can really read the vertex from this form. We know from these previous transformations right here, the -2 meant my graph moved to the right 2 units, right? And the +1 meant up 1. So my vertex here was at 2, 1. So I can hopefully see how this form tells me what the vertex is. This form, the vertex is going to be at HK, right? So the opposite of what H is, right? If it's X minus H, then it's just H. If it was X plus H, then it'd be negative H, right? And then K. And that's just from the transformations, right? So it's just from how this graph moves. It moves to the left or right based on H, and it moves up or down based on K, right? And that's where the vertex goes. So the other component here is this A. A determines two things, actually. Number one, if A is greater than 0, the parabola opens up. If A is less than 0, the parabola opens down. Okay. So, and that is from our reflections. If you multiply a function by a negative, it flips all of the values down below. Number two, A stretches or compresses the parabola by a factor of A. Lots of quotes there, maybe more than grammatically necessary, right? But stretching and compressing aren't really technical math terms, right? And if I don't put the quotes around A, then it looks like I just forgot to finish my sentence, right? By a factor of A. So the A, if you remember from our transformations, when you multiply, that stretches the graph up if that multiple is bigger than 1, and it compresses it or sort of cuts it if it's a multiple less than 1. Mostly we will be stretching just because it's a little easier to show. So let's see an example then of this form. Let's let f of x equal -2 x plus 1 squared minus plus 2. Okay. So number one, you have to recognize this is a parabola. It's got this form. And so whatever your answer is going to be, if you're trying to graph it, it better be a parabola, right? The shape of a parabola. The question is, which parabola is it? And where is it located? What does it look like? Right? And that's where these different values come into play, right? And every other parabola in this form will have slightly different values for those three spots, okay? The +1 and the +2 tell me where the vertex is. It's going to be at -1, 2. And you can just memorize that, or you can also think of transformations, right? Even though there's some other stuff going on here, the +1 and the +2, that +1 shifts it over to the left because it's a +1, and then the +2 shifts it up. Let me give myself a little bit more room here to work. Over 1, up 2. So my vertex is there. Okay. And you'll see some questions that just ask you straight up, what is the vertex? And you would answer -1, 2. The next is looking at this. Right? That's my A value. Since that's a negative, it opens down, guaranteed. The last part is possibly the hardest part. There's a 2 there, so that means it's stretching the parabola by a factor of 2. It's easy to see that, and it's a good idea to say that, right? Stretch by 2. It sometimes is a little harder for students to actually graph that, but it doesn't have to be. Remember, from the vertex, we would normally go over 1 and down 1 in this case because it's a negative. But the 2 means I'm going to stretch it by 2. So I'm going to go over 1 and I'm going to go down 2 this time. Over 1, down 2. And what I get then is a parabola that is narrower than my regular parabola. When you're graphing these on My Math Lab, you'll need to do 2 points. So you'll click the parabola tool, you'll click the vertex first, and then you have to pick another point for your second point to graph the parabola. And I would highly recommend, figuring out what one of those points are, and that will create and finish your parabola curve. The other thing to warn you about on My Math Lab is they are very interested in this line of symmetry down the middle. I'm less interested in that. It's there, but we can kind of see it without even really focusing on that line. But in My Math Lab, they will want you to put this line in your graphs. I always get questions of students who are like, well, I've got the right parabola, but it's marking me wrong. Most of the time, that's because you just forgot to write in that axis of symmetry. The axis of symmetry is a vertical line. So that looks like x equals, and it always goes right through the vertex, which has an x coordinate of -1. So this is called the axis of symmetry. Right, and just watch out for that on your graphs and if you're finishing up that homework, because it's easy to overlook and frustrating. Okay. Questions about this kind of problem? Questions about any part of that? It really is work we've done before, but it's a little more sophisticated in that it's combining kind of lots of different transformations and stretchings, and it's focused on just this one type, this parabolic version. Now, unfortunately, not all parabolas come in that form. I'd like you to remember when you're working with lines, we love lines that are written, well, maybe love is too strong, but we prefer lines that are written in the form y equals mx plus b, I like to think of that vertex form as being equivalent to y equals mx plus b. Like all the good information is sitting right there for us. Yeah, good question. So on take-home work, it says find the x-intercepts, and that's also a problem that you'll have perhaps in some of the homework. On this one, it appears, again, my graph is kind of rough, but it appears that we actually were lucky and found the x-intercepts, right? Because from this point, if I go over 1 and down 2, that is on the x-axis. Now, in general, we are not going to be that lucky. So we'll have to do some algebra to find those x-intercepts. Remember, for any equation, if you want to find the x-intercepts, you're going to set y equal to 0, right, or f of x. So in this case, to solve the x-intercepts, I need to solve that equation, right? I want to find the x values that make y 0. Those are exactly my x-intercepts. When you have an equation that is in this vertex form, you can square it out and factor, use the quadratic formula, but it's actually easiest to use the square root property because it's already got this like perfect square bit. So I'm going to move this 2 over. I'm going to divide everything by minus 2. Then I can use the square root property and say x plus 1 has to equal the square root of 1, or x plus 1 equals the negative square root of 1. Right, that's the square root property. And here when we subtract the 1, I get x equals 0. And here I get x equals minus 2. And notice those do match up with those points. So you will want, if it asks you specifically to find the x-intercepts, you will want to find the exact values. They may be square roots, you know, not whole numbers. That's fine. They're still the x-intercepts. Notice there's not always an x-intercept, right? If my graph looks like that, there's going to be no x-intercept. If you try and solve for the x-intercepts, you're going to get imaginary values in that situation. Does that answer the question? That one? Okay, yeah, good question. So you don't really need the x-intercepts to graph. I mean, it's helpful because it's 2 extra points on your graph, but it's often easier to find other points instead of the x-intercepts. So, you know, this strategy of kind of counting over and down is a easier way of finding another point than the x-intercepts. But if the question asks you for x-intercepts, we do want to be able to find those. Okay, so we perhaps prefer that vertex form, but it is not uncommon for us to run into quadratics that are written in standard form, which is this. We kind of like this form when we were doing like the quadratic formula and stuff, but unfortunately it doesn't tell us exactly what the vertex is quite as easily as the vertex form. Now it does turn out that if you do some kind of fancy algebra and completing the square, you can make this look like vertex form. it turns out if you did that, this middle piece here would be, or this inside piece would be b over 2a. And this last piece, this constant that you get, it turns out it's kind of complicated to write it out. So I like to just think of it as f of, well, that's not even right. Scratch that. We'll just say that's something. We don't really want to actually complete the square because it's pretty complicated algebraically. You've got this a to keep track of, and you've got to work all on one side, and so instead what we really want to do for this is remember this little formula. This little fact here turns out to be the key to unlocking what this quadratic looks like. So notice the a here, it is the same as the a there. So it has the same function as the previous a, up, down, and any stretching. Okay, so that's just as good, right? You can see the a just as easily there as you could on the vertex form. So the only thing we're missing is the vertex. And it turns out the vertex is going to be at, actually, if you do complete the square, you get plus there, right? Because the vertex is negative b over 2a, and then f of negative b over 2a. And we certainly could spend some time to show and do the algebra to show why that works. I don't think you guys will love that. And I don't know that it really is going to gain a lot of knowledge for you, right? But perhaps you can imagine doing the completing the square and rearranging it and making it look like this. And so if you do, that would then tell you that the vertex is at this negative b over 2a. So either way, I'm just going to take this, this fact and use it to find the vertex. So let's see an example. F of x equals 2x squared plus 8x plus 7. Okay. This is a quadratic, so we know its graph is a parabola. The question is what parabola? And you can, I think it's always easiest probably to start with the vertex. Remember, the vertex is an ordered pair. So I need the x and the y, but when it's in this form, I need the x first. And the x comes from this formula. Negative b, so that's negative 8, over 2a, which is 2 times 2, or 4. So that's negative 8 over 4, which is negative 2. That's the x value of the vertex. To find the y value, well, the vertex is on the parabola, so that's what I plug into this function, right? That's what I'm representing with this. Whatever x I find here, I plug that into the function, and that'll tell me what the y value is. So 2 times minus 2 squared plus 8 times minus 2 plus 7. That's 4 times 2, which is 8, minus 16 plus 7 turns out to equal minus 1. So my vertex is at, my vertex is at -2, -1, which is down there. My second parts are I need to figure out what the 2 does. Since that's a +2, it opens up. And since it's a 2, that means it stretches everything by 2. So that means I would go over 1 and up 2 to find my sort of second points and third point. Okay. It's not a very accurate graph, right? I kind of missed the vertex, but notice here the x-intercepts are not so clear, right? I can estimate this x-intercept is somewhere between -1 and -2, but I'm not positive what that is exactly. I would need to use the quadratic formula in that case, right? I would set this equal to 0 and solve it with the quadratic formula if I needed the x-intercepts. It does turn out another really easy point here is the y-intercept. When you have a standard form like this, the y-intercept is f of 0, and so that is very easy to calculate, right? F of 0 is 7, so it's kind of off my scale, right? But that is another way of finding another point. So when you're graphing these parabolas, you need to figure out where the vertex is, but then you also need to figure out kind of how wide or narrow it is, and that's why you need that other point or other value. Yeah, like, so the question is like how to graph the A. Like what does that A value do to the graph? Remember my original parabola that hasn't been stretched or compressed at all? I would go over 1 and up 1. So it would look kind of like this. But the 2 in front, it turns out, stretches it. So it takes all of my normal values and doubles them, or doubles the distance from the vertex. So now instead of going over 1 and up 1, with the stretched version, I go over 1 and up 2. Right, and that hits here. Right, and this one I go over 1 and up 2. I really only need one side because it's symmetric. It's going to do the same thing on either side. And that's where I get this kind of stretched or more narrow version of the graph. Yeah, and so it's most common with values like 2 or 3 or 4, because those are easy for us to find the other points on. It works for fractions too. It just is a little harder to plot on a graph, right? So if it was 1/2, well, I'd go over 1 and up 1/2, and that's fine, right? That's not really any harder to do. It's just that it's just harder to find that point, right, on the graph. So it works actually for stretching and compressing. And it's the same process with either the vertex form or the standard form, that A. The only difference between the two is finding the vertex. Okay, so with the vertex form, right, that's the vertex form. Oops. The vertex is at HK. With my standard form, the vertex there is at -b over 2a, f of -b over 2a. And you know that you can just remember it, that's fine. But you may need to write that down, right, as a little formula. This one you can kind of come up with. If you remember the transformations, that's exactly where this vertex comes from. So this is one I think is kind of less important to memorize, but you'll want to know both of those. you do not need to turn one into the other or back and forth, because I can find everything I need from either form, right? So there's no purpose or value in us trying to change them back and forth, right? You can just keep them. If you're given the vertex form, work with the vertex form. If you're given the standard form, you say, well, I'd rather have the other one, but it's okay. I can still figure out where the vertex is. Then that A value is going to work the same for both of them. There are, I think, just a couple application problems with these. I think all the application problems are based on the idea that since it's a parabola, it has a max or a min. So if you have some physical property like throwing a ball or your profits or something, you're interested in kind of the max value, right? Or there's certain situations like a chemical reaction or something, you might be interested in the minimum value. If your model is a parabola, like one of these, then the max or the min that occurs at the vertex. The vertex. Do remember with those, anytime you're working with a application, you got to keep track of what X represents and what F of X represents. So if it says find the number of cars, well, that's potentially an X, right? But if it says find the profit from making the number of cars, then that's potentially, the Y value. This might be a better profit curve, right? So you find the right number of cars to make so that you maximize your profit. But otherwise, there's not too much to the applications. They're not maybe as so much like the other application problems we've seen. You're given the quadratic relationship, and you just want to identify that the vertex is the max or the min. Okay. Any questions? Guys, feeling good?